presentation.
Thank you. Thank you for the introduction. So my name is Jean-Marc Robert, and I represent you this work entitled RISC-V word-size modular instructions for RNS. So the motivation of this work, we are working on modular multiplication for large numbers. As it was said, it's mainly in use cases like classic cryptography, RSA, elliptic curve cryptography, pairing-based cryptography, post-quantum cryptography for homomorphic protocols, isogeny-based protocols. In this kind of primitives for cryptography, the modulus sizes range from a few hundred to a few thousand bits. And so for fast and secure computation, exotic numbers are often a good option. The residue number system is widely used, especially in the hardware implementation context. But indeed, so what is the residue number system? So you want to represent an integer x. So you represent it by its residues. The residues. So you have some mi, and the set of the mi is the RNS base. So the range of the system is the product of the moduli. The interest of this number system is that the computations, the arithmetic operations, are done independently on each channel. That is, there is no carry propagation, and it can be fully parallelized. That is a great advantage in case of hardware implementations, obviously. But what is also to be noticed is the linear complexity in terms of word operation, especially in the multiplication case. And so the number of moduli is set according to the size of the modulus you want to compute, the modular reduction. Just a small toy example to show what is the RNS. So you have here a small base with three small modulus. Their products gives you the capital M, which is the range of the system. And so if you have two integers, if you, for example, compute the addition, you can check that the addition modulo the moduli gives the same representation of the result. The result is the RNS representation of the result. And so you see that the results of each operation is computed independently on each channel. One issue is the choice of the moduli in the base. A classical option is to use moduli with special form called the pseudo-Mersenne. The pseudo-Mersenne moduli, each mi is of the form 2 to the power of w minus some ci, a small constant. This allows to compute efficiently modular reduction at the word level, avoiding the computation of a costly division. You trade the costly division by a handful of multiplication by small constants, some logical operations, and a few additions. And so it's faster than a division, especially in the case where you don't have a division instruction in your processor. So how do we compute modular multiplication on big numbers using RNS? The approach is similar to the Montgomery modular multiplication. if you are not familiar with this approach, the main idea is to trade a big division on big numbers to compute the residue, the result of the modular operation, by a division by a constant which can be faster. And so you need in this case two bases, because the result of the multiplication obviously overflows the range of one single base. So like in the Montgomery approach with a classical representation, you can see here that we compute a sort of quotient, but modulo the range of the first base. And so we need this result in the other base in order to compute the division, the exact division you see here. So this makes we need the first extension base here. We compute the cheap division in the second base, but since we need the result of this exact division in the other base, so this is the second base extension. The problem with base extension, as we will see, is that the complexity is quadratic in this case. So how do we perform base extension? The classical approach is to compute a conversion to an intermediate representation, and the forward conversion to go back in RNS system in the targeted in the destination base. So these operations can be interleaved and parallelized in some way. So the two approaches in the literature, you have the proposition of Sabo and Tanaka, which is quite old, using mixed radix representation, or the other way is to take advantage of the Chinese remainder theorem, and Kawamura and Al propose an approach to compute efficiently this formula, and we compute the moduli of the destination base. However, the complexity is quadratic, because this formula is computed for each moduli of the destination base. And so, if we look at the complexity, we see that it is quadratic. So it's quite similar to the complexity of the classical in the classical representation case. The difference is that we have the penalty of big constants here. You can see here those big constants are the cause of this. It's the use of the modular operation at the word level in each channel for the RNS base, because even with pseudo-Mersenne's moduli, there are more operations than in the multi-precision case. And so those big constants, if we want to deal with them, so we will have the penalty of this constant, and it renders the computations quite slow in comparison with classical representation. And even if we take advantage of parallel implementation with the rise of the SIMD extensions in most of the modern processors, you still need a lot of time to compute, and it's not even in this case fast enough to be competitive. And so what if we could speed up the computation with dedicated instructions at the word size, at the word level, so compute modular arithmetic, with specific instructions. The goal is to diminish to make the constant lower. And here comes the RISC-V. The idea is to take advantage of the open instruction set architecture. So there are some fixed, the instruction format is fixed, obviously, but even with the standardization, we have some place. There are free opcodes you can use to design custom instruction set, provided you keep the good format for the instructions. And so we will implement word size modular operations with the specific instructions. The first step of this work, we are in the context of sequential implementation. So in this work, as we will mention later, we won't take advantage of the RNS parallelization possibilities, but it's just to check that we can lower enough the constants. And so in the simulation process, we had two steps. The first is just a functional simulator to check if the custom instructions provides good results and to develop the source code for the computation, the modular multiplication. And in the second step, we use the GEM5 simulator, which is an architectural simulator. This allows to simulate the micro architectural features like in order, out of order, pipelining, cache memory, and also to run the simulation cycle accurate, and therefore to be able to compare performances and timings of the computations. So in our custom instructions, we took the approach to have 3 sources and 1 destination. This is allowed in the standard, for example, or it is for the SIMD and the vectorized instruction set. So we have 3 instructions: the modular multiplication, the modular addition, and the subtraction, modular subtraction. Both operands in 2 source registers and the moduli in the third source. And in the simulation, so we want to compare and to evaluate the speedup with references, and the references are 2 configurations. The first, in a C code, you can write the operation, the modular operation, the reduction, and in this case, the compiler implements a division. So it can be very slow if your processor don't have a division extension. So we compare also the second version with the pseudo-Mersenne moduli. And we compared these 2 references with the version with our custom instructions. We combine this with 2 base extensions. So this sums up to 6 variants. The combination of the 3 configurations for the word size, the word modular reduction operation, and both base extensions. There are also other simulation parameters. obviously the RNS base size. We can set the latency of the instructions in the simulator, and so that's what we do. And we mainly have tested two configurations with short delays or long delays. In the short delays case, roughly the modular instructions we add in the instruction set have roughly the same latency of the conventional operations, which could be seen as a little optimistic, but we have tested also what we call long delays with so in the case of the surface budget on the chip is not large enough to have fast instructions. And also the microarchitectural features in order and out of order. The cache memory also is as you can see. So the total number of simulations is nearly 3,000 different configurations. If we go to the timings as the simulator, as we can see the results in the simulations. The sketch shows you so the clock cycles, the clock cycle numbers in versus the RNS base size. So roughly the curves are you can see the quadratic behavior in the curves here. The slowest version, as expected, is when you let the compiler implement a division. And using pseudo-Mersenne, so the conventional implementations with the conventional instruction set, you can see that you have more than twice the pseudo-Mersenne configuration is twice as fast as the modular, at least. And so the dark blue curves here shows you the timings of the configuration with our custom instructions, the word size modular operations, and we can see a speed up here, which is roughly around three times as fast as the pseudo-Mersenne configuration for the versions with our custom instructions. So we see that the Kawamura base extension is slightly faster than the Sabo and Tanaka, so the mixed radix base extensions. The Yarshi is the same, so the speed up is quite independent versus the base extension used. If we go into the numbers, so in this table we have the 64 moduli for the base, the RNS base, with the fastest instruction, so in short delays, two versions in order and out of order. So what you can, as a takeaway, the order of magnitude of the speed up in this case is it's around 3 for the fastest versions, the pseudo-Mersenne with Kawamura and our instructions. So the fact to replace the pseudo-Mersenne computation by a processor instruction, you speed up by 3. So this confirms that we have divided by the roughly this value, the big constants I showed you in the complexity evaluation. So you should say yes, but with your the long delays. What if we have slow instructions? And so what is interesting here is that even with slow instructions, so it's the same configurations except the delays of the instructions. For the best configuration, the speed up is around 2.3. So, as a conclusion, our goal was to design and to check how we can develop and implement fast and secure computations of cryptographic primitives. And so, the first step is the RNS sequential implementations, and with the conclusion with our custom instructions, we can see significant speedups, and so we confirm the interest of specific word size modular operation instructions in the context of the RISC-V processor, because it was the target of our simulations. What are the future works? So we want to improve the instructions and use two source instructions using one of the destination as an operand. So it's commonly used in cryptographic computation when you have a chain of computations, several operations, one after another. But so the interest of the RNS is to have parallel computations, to take advantage of the parallel possibilities of the system. And so what we aim also is to implement SIMD instruction sets with the word size modular operations in order to take advantage. And in this case, our hope is that RNS computation will show good performances in comparison with classical multi-precision libraries, especially also giving perhaps an advantage also in terms of security. So faster and more secure. And the last step, obviously, it is to make hardware implementation of the instruction set and test a full RISC-V processor if possible. That's all for me. Thank you very much for your attention.
Thank you both for presenting. We have some questions here in the chat.
Yes,
but I'm going to ask the first one that's not there. So it's one question that I have. So given that you had a lot of good results, do you have any intention, for instance, to join a task group and propose improvements on what you have today as part of the RISC-V standard itself?
Sorry, I'm not sure I have well understood the question. When you are talking about groups, what do you think?
Working groups within RISC-V International, the groups doing new or developing new extensions, for instance. So my question is more: do you believe this could be a good fit for the RISC-V as a standard? And if that yes, would you be ready to join and propose that kind of improvement on what we have today?
Yes, maybe my colleague will answer.
Yes, I can give you some answer on this. Actually, it was an estimation. This is the first work in order to estimate if this kind of function is really useful. We just limited our study on residue number system background, and more specifically on the modular multiplication application.
Just a quick one.
I'm not sure.
Speak near the microphone, because people are having a hard time listening to that.
Maybe I have to check my sound. Could you hear me?
Yeah, it's still kind of far away, so if you can speak near.
Maybe we will. Okay.
Yeah, better.
It's better. We are. It is a first work in order to estimate if it's a good idea or a good bad idea or a bad good idea. For the moment, we want to investigate more deeply in order to estimate if this kind of instruction is very useful. We want to try with only with two source instructions, like it has been chosen for in the last standard of SCMD instructions. And second, we hope to have FPGA hardware implementation of kind of RISC-V processor in order to have a good simulation and really have reliable results. And maybe we could see if we can join the team in order to see if it can't be standardized. For the moment, it's the beginning of the work.
Yeah, great. So we now have some questions from the chat, so I'm going to read them, and then you can try to answer those. The first one from Saad is basically how we can accelerate NTT computations using this.
If I understand the questions, in entity, in lattice-based cryptography, there are use of modular operation during the entity step. Here it's slightly different because in the lattice-based cryptography, the operands are, I think, 12 bits large. Here we are investigating quite large operands, word size operands of up to 64 bits. I'm not. Maybe it can be useful for entity, but I know that there are some other works that have been done in order to improve the entity on RISC-V processors, and also in order to perform this modular operation specifically in the entity. This work is for larger operands.
Another question I have here from Chris is whether this would also be helpful for lattice-based cryptographic implementations.
Yes, I see. It is quite similar to, well, it is the answer I gave previously, I'm sorry. But I see that there is also a remark about the benefit of Plantard arithmetic. We didn't compare our work with all the Plantard arithmetics. The point here is that with the Plantard arithmetic, there is a multiplicative constant that we have to deal with. And for this first implementation, we wanted to have more an implementation with no modular constant that is added to the result. We compared this with pseudo-Mersenne implementations, which are quite slower than the Plantard implementation, in order to see if using a specific instruction gives a real improvement or not. For the moment, we can see that it gives a significant improvement in the measure we made. Yes, we probably compare this with the Plantard arithmetics. It is a work that we have to do.
Another question from Saad here is how we can connect for joint work for implementing SIMD instructions and making a full processor. Maybe it's a invitation for collaboration.
Oh, it is. Yes, you can. I don't know if we put our email here.
Oh, I will.
Yeah, if you can do that, update the presentation, adding your emails. I can share that with all the attendees later. So you share the presentation with me, and then I share with them.
Yep. Okay. Yes.
Folks, do you have any more questions, folks, in the chat? So if you want to speak, just raise your hand or write that in the chat. No more questions? Okay, so I would like to thank you, Laurent and
Jean-Marc. Laurent Stéphane and Jean-Marc.
Oh, yeah.
I am Laurent Stéphane and it was Jean-Marc.
And Laurent, yeah, for presenting today. That's the first session. Thanks for the great insights. It's really, really technical, and that's really, really great one. The presentation is going to be available on RISC-V YouTube channel between today and tomorrow. I'm going to notify you all about the availability, and also get the slides with the data I'm going to share with you all who attended. Thank you very much for joining, folks. Thanks for starting the year with the great presentation. Thank you all for joining us today.
Thank you.